In this video, we're going to look at how to parametrize a two-dimensional ellipse in 3D space. Specifically, suppose you're given an ellipse with center HKN in R3, and that you know one major axis vertex and one minor axis vertex. This is enough to parametrize the ellipse. Using the center point and the major axis point, you can find the semi-major axis length using the distance formula. Similarly, using the center point and the minor axis point, you can find the semi-minor axis length. We'll call these A and B respectively. Since we have the major and minor axis lengths, we already know the equation of this ellipse in terms of UV coordinates that are centered at the center of our ellipse, where U and V are the unit vectors that we take to be a basis for the plane our ellipse resides in, and where U points along the major axis and V points along the minor axis. These vectors can be found by rescaling the vectors that point from the center to the major and minor axis vertices respectively to be unit vectors. If you recall the equation of an ellipse, it must be our ellipse satisfies U squared over A squared plus V squared over B squared equals 1, where real numbers U and V describe positions in the plane that the ellipse resides in, where we take vectors U and V to be our basis vectors. The question now becomes, how do we parametrize this ellipse? Well, remember how we parametrize a 2D ellipse in the xy plane. It's commonly parametrized by A cosine of t, B sine of t. If we change coordinates back to x, y, z, we get the following parametrization, which simplifies when we take into account the definition of vector u and the definition of vector v. Essentially, this parametrization says we want to add to the position of the center of our ellipse the time variable linear combination of vectors u and v that produce our ellipse centered at the origin of the uv coordinate system for the plane that the ellipse resides in. In this animation, you can see that this is indeed a parametrization of our ellipse. Now, what if we want to find an equation in terms of x, y, and z that our ellipse satisfies? Remember once again the definitions of vector u and v. We can use them to define the vector w as the cross product of u and v, so that we now have a new coordinate system UVW for R3. By the definitions of vectors UV and W, we readily get the transformation that sends UVW coordinates to XYZ coordinates, and inverting that transformation, we get the transformation that converts XYZ to UVW, the result of which we substitute for U, V, and W in the equation we know our ellipse satisfies in terms of U, V, and W, and we get the equation that our ellipse satisfies in x, y, and z. Note that w did not appear in the equation for our ellipse in uv coordinates. So in UVW space, our equation really describes a surface and not just a curve. It's the surface we get by dragging our elliptical curve in the w and negative w directions in 3D space. As a result, the equation we get in terms of x, y, and z will also not describe just the ellipse. It will describe a surface in 3D space that contains our ellipse, as seen here. That's it for this video. Thanks for watching.